Welcome. We're going to go ahead and solve an AP Physics C free response problem from 1997 that involves rolling without slipping. Okay, so we have a solid cylinder with mass m and radius r and rotational inertia 1/2 mr squared. Rolls without slipping down the inclined plane shown above. The cylinder starts from rest at a height h. The inclined plane makes an angle theta with the horizontal. Express all solutions in terms of m, r, h, theta, and g. Okay, so for A, we want to find the translational speed of the cylinder when it reaches the bottom of the inclined plane. So I always like to draw the point I'm looking at. So I'm going to find the translational speed right here. Okay, so if I look at this problem, it starts up here where its velocity is 0, and it comes down to here. Anytime something is changing positions and changing velocities, energy conservation is a great bet. So let's go ahead and label what type of energy it has at each position. So right here, it is some height above the ground, has no velocity, but it does have some gravitational potential energy. Now down here, okay, so it clearly has a kinetic energy. It has a translational kinetic energy because it is moving translationally. It also has a rotational kinetic energy because the cylinder is rotating. So it has both a translational and a rotational component. So now let's go ahead and set this up. And again, for energy conservation, we're always comparing 2 points. So it's initially UG, and then we have KE translational plus KE rotational. Great. So UG is just going to be mg and capital H in this case. KE translational is 1/2 m times v squared. KE rotational, we know that is the rotational analog to translational, so that's 1/2. I is the rotational analog to m, and omega is the rotational analog to v. Cool. So now let's go ahead. Again, we want to find the translational speed. Okay. So let me look to see things we're not allowed to have in our answer. We're not allowed to have I or omega, so let's see how we can get rid of those. I we know is 1/2 mr squared. Omega, so there's a relationship between linear velocity and angular velocity. That is going to be v equals omega r. So I know omega is going to be v over r. Let's go ahead and plug in those things we know now. So mgh equals 1/2 mv squared plus 1/2 I is 1/2 mr squared times omega, we just said, is v over r squared. Great. So now let's see. Cool. First thing off the bat, I noticed m is in every single term, so that'll just cancel. So I'm going to have gh equals 1/2 v squared plus 1/2 times 1/2 is going to be 1/4 r squared. V, this is going to be v squared over r squared. Cool. R squared, there's an r squared on the top, r squared on the bottom in this term, so those just cancel. Wow, this is fun. So we're left with gh equals 1/2 v squared plus 1/4 v squared. So I know 1/2 and 1/4 is 3/4 v squared gh, and then we can multiply both sides by 4/3. Gh equals v squared, and then I'll take the square root. So we got our good old answer. Okay, so let's go ahead and go on to point B and C. So for B, okay, looks like we got to draw a good old free body diagram. I love drawing these. So here's my inclined plane. I'll just draw that kind of small underneath. Great. So what forces do we have acting on the cylinder? Well, we have force of gravity, which we'll always draw from the center of the object. So we have force of gravity. We have normal force, and that is the point of application is going to be in contact with the surface. So that's Fm. And then we have force of friction. So that's going to be, again, in contact with the bottom of it. And in this case, if something's rolling without slipping, it is static friction that is helping it roll. Things cannot roll unless there's friction there. It's really, really hard to get your wheels to roll how you want them to on an icy day. And that's because there's not much friction on those days. Cool. So let's go ahead and go on to C. So we want to show that the acceleration of the center of mass of the cylinder while it's rolling down the inclined plane is 2/3 g sine theta. Okay. So we found velocity previously. It is a constant acceleration. We could use the constant acceleration equations, but I'm going to go ahead and try it a different way just for fun. So oftentimes if we want to find acceleration, we just drew a free body diagram. Forces is a great idea, and thinking along the lines of F net equals ma. So I'm going to go ahead and look at that. So let's go ahead and set up forces. So this is dealing with the translational motion of the cylinder. Great. So if we set that up, so it is accelerating, and we're going to go ahead and call this the y direction, this the x direction. So we're going to set up F net x. So if I go ahead and set up F net x, let's see. So it looks like I'm going to just redraw my free body diagram to the side, just in line with my new coordinate system. So we have force of static friction. We have Fg, which is what? Mg. We're going to have to split Fg into our x and y components. So we have Fgy is mg cosine of theta, and Fgx is going to be mg sine of theta. So again, we'll have Fn, we'll have force of static friction, and I just split gravity into my x and y components. Cool. So if I'm looking at F net x, and I'll say the direction it moves is the positive direction, I'll have force of gravity in the x direction, take away force of static friction. Okay, so F net I know is always equal to ma. Fgx is going to be mg sine of theta. Force of static friction, I'll just go ahead and leave it like that. We don't necessarily know what it is or know the coefficient. Cool. So I'm going to come back to that in a little bit. And again, it looks like I'm not allowed to have force of static friction in my final answer. I can only have m, r, h, theta, and g in my final answers. So it is rolling down the inclined plane. Anytime things are rolling, you're dealing with forces, we got to think about torques. Torque is the rotational analog to force. So let me just draw this over here a little bit, give myself more space for later. So actually I'll do it in a different color. So we have torques. So that's dealing with the rotational part of it. So again, we always got to start. So we started with F net equals ma on the other part. Now we're going to start with the rotational analog of that, which is T net equals moment of inertia times alpha. So now let's think about what forces are making this thing rotate. So normal force, if you apply a force like this up on an object like that, that's not going to make it rotate. Gravity is applied from the center. If I drop like a regular old water bottle, it's not going to rotate unless I like tie a string or apply another force to it. So gravity's not going to make it rotate, but friction is going to be tangent to it, and that's going to make it want to rotate kind of downwards. So the net torque is going to be force of static friction times the radius. The moment of inertia of this thing, and again, that's from previously, that is going to be 1/2 mr squared. So alpha is angular acceleration, but we want, if it doesn't say specifically angular acceleration, we'll assume we want linear acceleration. So we know the relationship between angular and linear acceleration is a equals r alpha. So I'm going to go ahead and put that in. So we have a over r. Great. So over here we have 1r cancels. So we have force of static friction times r equals 1/2 mra. Oops, we can cancel out one more r. That's fun. Okay. R's cancel, so we're left with force of static friction equals 1/2 ma. So now, cool. I have force of static friction over here. Force of static friction over here, I'm not allowed in my final answer because again, I can only have mr, h, theta, and g in my final answer. So I'm going to go ahead and put that on in here. So then we're left with ma equals mg sine theta minus force of static friction is 1/2 ma. Great, I'm solving for a, so I'll move everything with a onto the same side. So we have ma plus 1/2 ma equals mg sine of theta. I'm going to go up here, a little more space, so we have 1 ma plus 1/2 ma, so that's 3/2 ma equals mg sine of theta. Cancels out. And then a, let's see, multiply both sides by 2/3. So it's 2/3 g sine of theta. Awesome.